Alright, so today I'd like to share a presentation. Actually, this is my assignment for pharmacokinetic class. So me as a student need to present this material from a chapter entitled Drug Absorption Principles. So here the outline of the presentation. The first we will discuss about drug absorption and bioavailability, and then intestinal membrane transport, what else, the kinds of membrane transport, and then we will talk about primary and secondary factors that can influence drug absorptions. And then the last is about evaluation of oral drug absorption in human, and of course the summary. As we know, pharmacokinetics consists of four processes. The first is absorption, and then distribution, and then metabolism and excretion. As we know, absorption is the rate and extent at which drugs reach the systemic circulation from the site of administration, while for distribution is all the processes that are involved from the time when the drug reaches the circulation to the time when it or a metabolite of the drug leaves the body. While for metabolism is all the biochemical processes that result in a chemical change to the drug compound, including both the metabolism in the gut wall, the liver, the blood circulation. And the last process is excretion. As we know, excretion is the process in which the drug is eliminated from the systemic circulation into bile, urine, feces, sweat, and air. Here is we will talk about the relationship between drug absorption and bioavailability. Actually, drug absorption plays an important role in bioavailability determination since the drug absorption contributes importantly to the time and extent that drug targets exposure to therapeutic drug in vivo. So bioavailability can be mathematically represented by the equation here, as we can see. F is bioavailability, is equal to Fa multiplied by Fg and multiplied by Fh, which Fa is the fraction of drug absorbed, and Fg is the fraction that escapes metabolism in the gastrointestinal tract, and Fh is the fraction that escapes first pass hepatic metabolism. So, based on the equation, one of the main factors governing by the bioavailability of a compound or drug is the fraction of the drug absorbed. Here is two fundamental parameters govern drug absorption. They are solubility and permeability because we focus on gastrointestinal tract processes. So here is gastrointestinal permeability. So solubility and permeability. If both the drug solubility and permeability are enhanced, there will be a great increase in the rate and extent of oral absorption. So, therefore, the oral bioavailability of a drug is largely function of three of these: its solubility characteristics in gastrointestinal fluids, and then absorption into the systemic circulation, and the third is metabolic stability. Here we will talk about some types of intestinal membrane transport. Generally, there are two main intestinal membrane transport, even not only intestinal actually, many organs in our body. So this is general membrane transport, transcellular and paracellular. Transcellular consists of passive diffusion, carrier-mediated transport, and endocytosis, while for paracellular as the passage of solute without passage through the epithelium cells. Here we can see this is the part of membrane that called apical membrane. Apical membrane is the side of the membrane that faces the lumen of gastrointestinal. While here, this is the basolateral membrane This is basal membrane and lateral membrane, so we call basolateral membrane. Basolateral membrane is the membrane that faces the blood circulation. So this is the membrane, and this is apical membrane. Here is lumen intestinal lumen, sorry, and then here is the blood circulation. And this is the transcellular route, and here is paracellular route. So paracellular route is the route in between um, the cell of the membrane, while transcellular route is the road that go through the cells of the membrane. The first here is passive diffusion. Passive diffusion, as we can see, is the part of transcellular. Okay, so passive diffusion. For passive diffusion, as we can see here, intestinal lumen here, this is the membrane, and this is the drug or a blood circulation, and this is the cells that receive the drug. Here is the transcellular active, transcellular passive, paracellular, and endocytosis. So this is the part, some parts of the membrane transport. So generally, hydrophobic molecules can pass through to lipid bilayers. Lipid bilayers is the membrane. Actually, by random molecular motions. So any drug that have the characteristics of high hydrophobicity actually can go through the membrane by random molecular motion. It can be active transcellular or passive transcellular. And the direction of mass transfer of molecules or substances by passive diffusion depends on the concentration gradient on the two sides of the membrane, of course. While for lipophilic compounds are generally absorbed by passive diffusion through the intestinal epithelium. So here, for hydrophobic molecules, can go through the lipid bilayer or the membrane by random molecular motions, while for lipophilic compounds are generally absorbed by passive diffusion only. Here, for the passive diffusion, actually the molecules is governed by Fick's first law. What is Fick's first law? So here the representation or the description actually for the transport of the drug from GI gastrointestinal. This is the membrane and this is the blood. So here is J. J is the flux or the amount of material or the drug flowing through a unit cross section. So here the flux here, the amount of material flowing through a unit cross section. So the flux is equal to D. D is the diffusion coefficient or diffusivity. The measurement is centimeter square per second here. Multiply by C1 minus C2. C1 is the drug concentration at membrane wall in intestinal lumen, and measurement is per mole, while C2 is the drug concentration at membrane wall in blood site. So here you can see this is the membrane or apical membrane, and here is the basolateral membrane. So C1 is the concentration of the drug at the membrane wall in intestinal lumen here, while C2 is the drug concentration at membrane wall in blood site. So because here is the blood site and here is the intestinal lumen, okay, and divided by H. H is the membrane thickness. Well, here I'll explain this in the next slides. Here the assumptions of this equation, or the J, the Fick's first law, the assumptions made by this model are the following. So the first, the steady state flux. So this is the first assumption. that can made by the model of the flux for Fick's first law. So the transfer of drugs reaches to steady state very fast. And second assumption is the steady state follows same conditions, where both sides of the membrane are well stirred and homogeneous. So, define partition coefficient or K. This is new terminology. Maybe you ever heard this partition coefficient, or we call K. K is equal to C1 divided by CD. Okay, and equal to C2 divided by CR. C2, as I mentioned previously, C1 is the drug concentration in the lumen site, while C2 is the concentration of the drug in blood circulation site. And here, CD, a drug concentration in the gastric intestinal lumen, while CR is the drug concentration in the blood. Okay, C1 and C2 is the drug concentration in the membrane in different sites. Okay, but C, D, and CR is the concentration of the drug in the gastrointestinal and in the blood, respectively. So here we can convert the J or the flux is equal to day multiplied by KCD minus KCR divided by H. Or here we can simplify into day K multiplied by CD minus CR divided by H. If CD is much larger than CR, then J is day K multiplied by CD divided by H. Only because we neglected the CR, because CR is very low in comparison with CD. Divine permeability coefficient we call P. P is permeability coefficient. So P is day K divided H, or diffusivity, and then K is the partition coefficient, and H is the thickness of the membrane. Then J is equal to PC. PC is permeability coefficient. Permeability multiplied by the concentration of the drug. And consider the absorptive surface area. We can get the final equation for J. dm per dt is equal to J, or the flux. So the flux is equal to permeability multiplied by A. A is the surface area of the membrane, multiplied by CD minus CR. CD is the concentration of the drug in the gastric intestinal, and CR is the drug concentration in the blood. So we can get the J or the flux actually by only know some characteristics of the membrane, the permeability of the membrane, and then the surface area, and then we can collect it, the drug in the gastric intestinal, or the dose of the drug that we consume, and then CR is the concentration of the drug in the blood. So we can collect the drug or the blood, and then we can measure how much the drug in the blood circulation. And then this is the second membrane transport of transcellular, called carrier-mediated transport. So intestinal epithelial cell membranes are highly polarized. Here is we all already described previously, apical membrane and basolateral membrane. The apical membrane faces the external lumen with many microvilli to increase the membrane surface area. So many membrane transporters are located in the site, facilitating absorption for most nutrients and many drugs, while basolateral is toward the blood circulation here. For carrier-mediated transport, actually depending on the direction and category of transported solutes, drug carrier to mediate transport can also be classified into unipolar, simpolar, and antipolar. Where unipolar is the carrier-mediated transport with single solute, And then Simporter facilitates the transport of two solids with same direction, while an antiporter facilitates the transport of two solids with opposite directions. And based on the concentration gradient of the solids and energy involved in the process, drug carrier can be classified into two classes: facilitated diffusion and active transport. So here we will discuss first for facilitated diffusion. So facilitated diffusion is the part of carrier-mediated transport. In facilitated diffusion, carrier proteins are involved. Carrier proteins here as the transporters. So in facilitated diffusion, um, it's different from the passive diffusion, because in facilitated diffusion we need carrier to transport the drug. And then in facilitated diffusion doesn't need energy. So this is actually similar or just like the passive diffusion, right? And then, similar to passive diffusion, transport direction depends on the solid's concentration gradient, um, from higher concentration to lower concentration, of course. However, facilitated diffusion has higher transport rate than what would be expected from passive diffusion alone. Do you know why? Because we need this is a help of carrier protein. You can imagine when we just go to some or a place just by walking, and someone go there by maybe a car or a bicycle. Of course, when he or she use a transporter, it will be faster, right? So here the facilitated diffusion has higher transport rate than what would be expected from passive diffusion alone. Okay, so the second part of carrier mediated transport is active transport. The primary mode by which molecules are transported against electrical and or chemical concentration gradients is the definition of active transport. So here for active transport, the process involves a membrane-bound protein molecule that binds reversibly to the solid molecule at a specific site. The complex then undergoes a change in conformation that translocates the solute to other side of the membrane. Here are factors that can affect active transport. So it needs energy, and then of course it's influenced by temperature and then stereospecificity of the molecule. Similar to enzyme kinetics, active transport also exhibits saturable kinetics and can be inhibited by similar structural analogs. So it can be a competitive um, relationship with other similar structural analogs or other drugs. For active transport, probably you ever seen this equation. This is a Michaelis-Menten equation, but here we change the flow by J. J is the flux, so J is equal to J max multiplied by the concentration of the drug divided by Km plus C, or the concentration, where J is the drug flux, J max is the maximum drug flux, C the drug concentration, and Km is the drug affinity to carrier. And here there is two regulation. So at low concentration, where C the concentration of the drug much lower than the Km, or the drug affinity to carrier, so first order absorption prevails, and therefore the J is equal to J max multiplied by C divided by Km. Okay, because we neglected the concentration, because the concentration is much lower than km. But at high concentration, where the concentration of the drug much higher than km, or the drug affinity to carrier, so zero order absorption prevails, and therefore the flux is equal to J max only. J max is the maximum drug flux. So here, as you can see, this is for active transport and this is for passive transport, because they have no saturable kinetics, right, for passive diffusion. But for active transport, because there is also can be competitive with other drugs, and to bind with the carrier or the protein transport, so it can be saturable condition. So here is the graph of the active transport of the drug. In contrast to passive diffusion, drugs with active transport absorption mechanism may have a concentration dependent and or dose dependent absorption. So drug flux can be competitively inhibited by other substrates. So if you consume two drugs that have the same transporter, it can be competitive relationship between them, and the drug can be inhibit um, the binding of the drug and the protein transport. And here is the third part of carrier-mediated transport, okay, endocytosis. So endocytosis is a process in which a substance or compound gains entry into a cell without passing through the lipid cell membrane. And based on the mechanism and molecules involved, this process can be subdivided into different types. So it can be phagocytosis, pinocytosis, and receptor-mediated endocytosis. Here are the difference. So here is phagocytosis here, and then pinocytosis and receptor-mediated endocytosis. In each case, endocytosis results in the formation of an intracellular vesicle by the invagination of the plasma membrane and membrane fusion. So here is membrane fusion and form a vesicle here. Drug molecules can be transported into the cells by this process. So the drug not only by passive diffusion, not only by carrier-mediated transport, but also can by endocytosis. So endocytosis is the part of transcellular membrane transport, not the part of the carrier-mediated transport. They are different. So there are three transcellular here. There are three transcellular membrane transport: passive diffusion, carrier-mediated transport, and endocytosis. So here is the third, not the third, but the second membrane transport, the second general membrane transport, which is paracellular transport. Paracellular transport refers to transport solutes in between cells. So in between cells, without passage through the epithelial cells themselves. It is now well recognized that the intercellular junctions between epithelial cells of capillaries are leaky here, so allowing paracellular transport of small molecules to go through the leaky here. Paracellular transport is passive transport. Passive means doesn't need energy. Follows drug concentration gradient just like passive diffusion, and doesn't require energy. I have mentioned before for this. So now we will talk about which absorption path dominates drug absorption. So although different mechanisms of oral drug absorption have been shown in small intestinal regions under physiological conditions, Several routes may contribute to drug absorption at the same time. So a drug can be transported by passive diffusion or can be in the same time can be transported by endocytosis or other membrane transport. Okay, but usually the fastest route dominates the absorption of a particular compound. So even though a drug have multiple membrane transport mechanism, but actually the fastest route will dominate the absorption of the drug in the membrane of the absorption site. So in general here, passive diffusion is the main mechanisms for absorption of many lipophilic compounds, while the carrier-mediated process governs the absorption of transporter substrates. And in some cases, paracellular junction is the route for the absorption of some small hydrophilic compounds with molecular weight less than 300. So we can actually predict it from the characteristics of the drug. For example, whether it's lipophilic compounds or hydrophilic compounds. If it's small hydrophilic compounds, we can see the molecular weight of the drug. If it's less than 300 of the molecular weight, so it can be transported by paracellular routes. So probably for the first term here, I only discuss until this part, so we will continue to another part in other session. Thank you.